All right, so first of all, I want you guys to give me the very generic reaction mechanism for an, it's electrophilic aromatic substitution reaction. All right, super duper. Most important thing is first step. Who's my nucleophile? Who's my electrophile?
Benzene's a nucleophile, and then that ion is the electrophile.
Yeah, right. In these reactions, in your electrophilic aromatic substitution reactions, your benzene is playing the role of the nucleophile, right? Most important thing to get right. So that pair of electrons will come up there. This is going to create an intermediate where the carbocation is on the carbon that didn't just get that addition on there, right? On the one that lost that double bond. So then the next step is, or rather the last step, I have some generic base, which is going to come and grab that hydrogen, and that pair of electrons can return back down, forming my aromatic compound. Cool? All right, now take this guy here and label those sites either being ortho, meta, or para. All right, so remember OMP. Say it like a Valley girl, and then it sticks in your brain. Going outwards, the ortho sites are the closest, the meta sites are the next one, and then there is just the one parasite. Right, and remember this is important because when you're starting out with a naked benzene, obviously it doesn't matter which one of those 6 hydrogens you substitute. But if you're starting out with a substituted benzene and you go another round of electrophilic aromatic substitution, those different groups have a tendency to direct to the different positions. Okay, so let's take a look at a few of these different substitution groups here, right? So this is going to be when Y equals, I'm going to put down a bunch of different groups and you're going to organize them in terms of being either strongly, so we'll go strongly activating all the way down to strongly deactivating. With like the midpoint here being when Y equals just a hydrogen, meaning just a naked benzene ring here, right? But your job is going to be, I'm going to put a bunch of groups down. You're going to put them where they are on this continuum here, okay? All right, so let's go with oh, it's 18 and 19. Whoops. Oh, yeah. Oh, doesn't make any sense. Gotta have a hydrogen there. All right, and then once you've ordered them along this little continuum here, go through and indicate which ones are going to be ortho-para directing and which ones are going to be meta directing. Cool. All right, so which one of our groups is the strongly activating ones?
The aniline.
Yeah, so aniline, so the amine group, and then sort of tied is going to also be the OH group. Remember, what makes these strongly activating is that both of those substituents have those pairs of electrons that they can lend to the ring, which is going to make benzene an even better nucleophile, right? It's just pouring electrons into that benzene ring, making it even more, of a negative, well, not negatively charged, but whatever, electron densities greater in the ring. What's next?
The methyl group is a weak activator.
Yep, so the methyl group is sort of like kind of along this line here. So now we're at weak, but still activating. Here's weak, but still deactivating. In the middle is this amino group. Okay, amino groups, they have these pair of electrons just like an amine does, but then it has this carbonyl group that's also kind of pulling electrons towards it as well. So it's activating, but it's not as strongly activating as an amine group. Okay, what about our weak deactivators?
The carboxylic acid.
The carboxylic acid kind of sits in the middle here. The weakest that we have is actually our halogen. All right, so if you're halogenated a ring, that's a weakly deactivated ring. Next, you have your carboxylic acid group. This is any carboxylic acid derivative would also, if you had a ester group, but it was going the other way. So I guess let me explain what I mean by that. Right here, my benzene ring is over here. I could put also in this category would be an ester group. But if my benzene ring is over here next to the carbonyl group, that makes it deactivating, right? So that carbonyl carbon is deactivated. It's pulling electron density away from that ring. And then strongless deactivator is the nitro group, you know, also just to keep in mind that sulfonyl group was also in that category as well. Those are our strong deactivators. They are like maximally electron withdrawing. Okay, and then if I'm going to categorize ortho-para directors, that's all of my activators as well as those halogens, right? Halogens are this weird like category where they're deactivating, meaning that they're less reactive than a benzene ring when it's all naked, but nonetheless, they're still ortho-para directing, right? So this is ortho-para directing. And then all of our other deactivators are our metadirectors. Okay, now this is important to keep in mind, not only whether a group is meta directing versus ortho-para directing, but where it lies on this continuum as well, right? So let's take, for example, an aniline, and I want to chlorinate that. I do just want to note that no, I lied. If I have a naked benzene ring, I have to catalyze this reaction, right? Why don't I need to catalyze it with aniline?
Because then the amine group donates electrons to make it a better nucleophile anyway.
Yeah, right. So this is what this activating means, right? Just makes it more reactive. So if I have an aniline, it's that much more reactive than benzene. I actually don't need a catalyst. And I'm going to get a mixture of products because this is an ortho-para director. Okay, but what am I going to get if I have first of all, take a second to name this guy as well. Oh, I get it. I want to go like this. So first of all, what's the name of this?
2-methyl aniline.
Yeah, nice. 2-methyl aniline. And so I wanted to do this example because here we have like a conflict between where our two substituents are trying to direct this incoming chlorine. We have our amine group, which is an ortho-para director, so it would love to put it either there or there. But we have a methyl group, which is also an ortho-para director, and its ortho-para would be either here or here. So who's going to win?
The aniline.
Yeah, the amine group, right? Because it is the stronger, right? So here's my methyl group down here. It's an activator, but it's a weak activator. My amine group is a strong activator. So what wins is the amine group. All right, so my incoming substituents would be directed either ortho para to whatever group is going to be stronger. Cool. And then what's the consideration if I'm going to go through and sort of label these major or minor products? Which one do we think is going to be the major product?
The amine group would still be the major product, wouldn't it?
The amine group. So I got the amine group in both of them. What do you mean?
The para.
Oh, you mean the major product between the two? My bad.
Yeah. Yeah, the para, right? So this guy's major. And why did you say that?
Well, chlorine's really big, and to add to the ortho side would be tougher than the para.
Yeah, right. Sterics. I mean, this isn't a terribly large group, my amine group, so you would still get a pretty decent balance, but nonetheless, you're still looking at like 52, 48. I don't know, I'm making up numbers, but the bottom line is it's still going to favor the less sterically hindered site. That's also the case because we only have one metasite or one ortho site because our other ortho site is occupied, right? The other consideration is the fact that you actually usually have two ortho sites compared to one parasite. Sounds like I'm saying parasite, but yes. Okay, so then there's sort of our generic nucleophilic. And then in terms of EAS, I want you guys to rank. Actually, I'm going to make it even more difficult. Benzene, pyrrole, and pyridine. Draw me these structures as well. Pyrrole is the 5-membered nitrogen heterocyclic ring. Pyridine is the 6-membered heterocyclic with nitrogen. Which one's the best, the most reactive towards electrophilic aromatic substitutions?
The pyridine?
No. Pyrrole. Pyridine is the worst. Okay. Pyrrole has this nitrogen which has this pair of electrons that's actually participating in the aromaticity of that ring. The pair of electrons on pyridine is not participating in that ring, right? These guys live in an sp2 orbital. So then if I'm going to chlorinate this guy, give me the products there. Where does it go?
On the meta.
Yeah, well, so you got to watch out, right? We can't say orthoparameta anymore with 5-membered rings. It's only something that really works with 6-membered rings. What you need to remember is C2, right? The carbon directly adjacent to that heteroatom is where that in-clubbing substituent is going to go. Okay? And we can do the same thing here, except for now we're going to have to use not only a catalyst, but also heat, because these guys are just so unreactive for electrophilic aromatic substitutions. In the case of pyridine, and this might have been what you were thinking, because we have a 6-membered ring, we can talk ortho-metapara. And just like with our other deactivators, this is a meta-director. All right, so pyrrole you want to think of as being just like an activated ring, whereas pyridine is a deactivated. All right, so now jumping to nucleophilic aromatic substitutions. I want you guys to draw me a generic reaction scheme for a nucleophilic aromatic substitution. All right, most important thing to remember with these is that the benzene has to have a good leaving group, right? This doesn't work with just a naked benzene ring. You have to have a good leaving group on there for it to be susceptible to one of these nucleophilic aromatic substitution reactions. All right. To be honest, if you thought about this as sort of happening in one step, I would forgive you. But really, we think of these as occurring because that negative charge is going to be stabilized by that benzene ring, right? By resonance. Okay, so then And right, so then the whole reason that we draw this intermediate is because if we were really good, we would draw out all those different resonance contributors that are participating in resonance with this structure here. We're going to be lazy and not do that. All right, and then this guy will come back down, kick off our leaving group. Cool. All right, so then let's take our same, at the bottom here. No. Take our same three compounds here, pyrrole, pyridine, and benzene, and I want you to rank them in terms of their propensity to undergo nucleophilic aromatic substitution reactions. All right, and hopefully we remember that this is the exact reverse of what it is for the electrophilic aromatic substitutions, right? Pyridine is actually going to be the best for these nucleophilic aromatic substitutions. There is one catch with pyridine that it's important to remember. Does anybody remember what that is? It only works if you're on like the C2 or C4 position. All right, so it doesn't matter if you have a good leaving group and it's on C3, you still won't have any sort of a nucleophilic aromatic substitution. So this compound up here, for example, would not be able to undergo nucleophilic aromatic substitution because the chlorine group is located at C3. All right, so that's the only catch with the pyridine. It's more reactive than benzene when it comes to these nucleophilic aromatic substitutions, but that leaving group has to be on carbon 2 or 4.
With NAS, it has to have a leaving group.
Correct, yes. Your hydrogen isn't going to work, right? Yeah, so I mean, typically it would be something like a halogen. There was one other one. Let's remind ourselves up real quick. And that is this diazium ion real quick. Real quick, I don't know why I said that. But yes, the diazium ion is another thing that we saw that plays the role of a good leaving group. And one of the reasons why this was so powerful is because we actually know how to make it starting from scratch here, right? Starting from a naked benzene ring. So you guys fill in these gaps in the middle here. What do I need to do?
Well, you can convert it into an aniline.
Got to get it to an aniline first. Yep, but you need to, and there's a step right before that too.
Nitration.
Yeah, right. So first, we're going to add nitric acid with our strong acid catalyst. This will stick a nitro group on there. How do we get our nitro? So then what do we do next?
So we're gonna use H2 palladium to get aniline.
Awesome, yeah. So then we gotta reduce our nitro group. And then very, very similar to what we had over here, but this is actually HNO2. This is nitrite, no. I don't remember what we call it. What do you call that? Nitric?
Nitric acid. Like
Yeah,
with an
nitric
OUS.
acid.
Like with a what?
OUS, nitrous.
Oh, yes. Okay, nitrous. Right. Except nitric. Okay, excellent. You also need actually HCl and 0 degrees Celsius is what you're going to see for that. All right, but this is how you take a naked benzene ring and prep it to be great for these nucleophilic aromatic substitution reactions. What else? Let's see. All right, just a few more sort of random reactions to go over that we learned in these same sections. Everybody see if you can't fill in the gaps here. All right, how do I get that ethyl group on there?
I used 1-bromoethane with aluminum bromide.
Yeah. All right. Typically, for whatever reason, but I think what's more common to see is the chlorines. I don't think it's wrong to use the bromide, but nonetheless, I don't think it's wrong to use an alkyl bromide, but what you will see more often is an alkyl chloride and then aluminum chloride. I told you guys, when you see this, AlCl3, what do you think?
Catalyst?
In both, so we see we see this aluminum chloride in two instances, both to catalyze reactions with alkyl halides, as well as to catalyze reactions with acyl chlorides. And in both cases, it's doing the exact same thing. It's removing that chlorine, creating a carbocation. So when you see AlCl3, you're thinking it's going to pop a chloride off there. Okay, so that's exactly what this does. Absolutely, so this will catalyze. This is a Friedel-Crafts alkylation reaction. Remember, in this case, I strategically chose it. It doesn't really matter, but you do have hydride shifts that are very common to see with these Friedel-Crafts alkylation reactions. Okay, again, in this case, it wouldn't be an issue, but just something to be aware of. And then how do I get to, we should be able to name this guy.
Benzoic acid.
Yeah, so how do we get to benzoic acid?
Potassium permanganate.
No.
Can we use water and acid?
No.
Chromic acid?
Yeah, chromic. So, right, this is where you use your like ultra strong oxidizer here. And it doesn't matter if this alkyl chain is 1,000 carbons long, right? It cuts it off at 1 carbon removed from that ring. So even though we started out with an ethyl group, we actually lose a carbon to this oxidation reaction.
I was going through the study guide for from the ACS website, and they don't use chromic acid for really any, well, I mean, they use the K2CrO7, but not the H2CrO4. So I don't know, like
K2CrO7. Yeah, that's, I mean, yeah, to be honest, our book doesn't, but I do know that you kind of lump these chromium oxidizers together. The chromium-based oxidizers are strong oxidizers. Yeah, I mean, to be honest, that sucks. I wish it was consistent, but yeah, I would kind of lump those two together in your mind.
okay. If I may, just one more question. What
Yeah,
what
absolutely.
exactly does permanganate oxidize then?
I mean, that is a great question. I mean, it is certainly an oxidizer, but I don't know. I honestly don't know where the line is in organic chemistry. I'll have to do like look that up a little bit, but unfortunately, like all we really can do is base like from what our book tells us. And so yes, I mean certainly potassium permanganate is an oxidizing agent, but right, I mean we've learned about so many like gray lines where on this side you need something stronger than on this side when you can get away with something weaker, and so I don't want to speculate as to where that dividing line is. I will say though, if you do see a potassium permanganate, you do want to think oxidation of sorts. Yeah, I wish I had a better answer for that. I don't know. You saw that a lot come up a lot in the ACS study guide as well?
Yeah, it was
Okay.
just it was usually an option between chromic acid and permanganate.
All right. Well, I will look that out and post an announcement as to like it could be very well be that like potassium permanganate is commonly used to oxidize this particular functional group, whereas chromic acid is used to oxidize this particular functional group. I just honestly don't know where that line is. So I'll look into that and see if there is some ultra common use for potassium permanganate.
Okay. The impression that I got was that
this group right here, real quick, Eric, I'll say that this group right here, an alkyl group, is just about the hardest thing to oxidize that there is. Right? So for that, I would certainly err towards the side of a chromium-based oxidizing agent, something super duper strong.
for sure, it like I looked it up and it did say that chromic acid was a much stronger oxidizer than
Yeah, that is
permanganate
like the
was.
top tier of like gonna blast anything with some oxygens.
Okay, cool. The impression that I got was that permanganate it oxidizes carbonyl groups rather than methyl groups.
Yeah, okay, and so that would make sense, right? If something that already has an oxygen on there is much easier to oxidize. But again, I don't want to say anything wrong, so I'm going to go through and look that up, and I'll make that clear, because there were a few things where the ACS clearly was using different reagents than we had learned about, and so I first of all went through to make sure that there were no reactions that were out of left field on the exam that I'm going to give you. But nonetheless, crap, there was one thing that I just thought, one more thing that let's just remember real quick, just because we're on this chapter. We found a new reducing agent, and this was like the Wolf whoever reducing agent, but see if you guys can't tell me what that was in order to reduce an acyl group next to a benzene ring. All right, you can use H2 in the palladium, but there was a brand new one that we learned about in this chapter that for whatever reason they love and seems to be more useful. Wolf Kushner or something like that. Kirchner.
Was it the H2N and H2?
Yeah, right. So this is H2N NH2. I think, yeah, under basic conditions with heat. Let me just show you guys what this thing looks like so it kind of makes a little bit more sense. So this is, you may have seen it written N2H4 or H2N NH2, but that's this compound here. Much like an oxidizing agent is usually sticking oxygens on that particular site, a reducing agent is sticking hydrogens. So this guy here is really good, a really good reducing agent because it really wants to become nitrogen gas, right? It really wants to get rid of those hydrogens so that it can be nitrogen triple bonded to nitrogen. Cool, yeah, all right. So now, yeah, you guys have any other questions? Open the floor here to anything and everything that we should review real quick. That's about all I got planned for you, but if you guys have any additional questions, we should go through those now.
Can we go over the ELIDE mechanism again? The phosphonium ELIDEs?
Sure, the
I know that's really random.
Flip, what was that dude's name? Didn't those are special? Yeah, anyways, so this is going to be all the way back in chapter 16. No, 17. Yeah, where? Didn't they have a special name? These are the ones that didn't work when we actually tried to do them in the lab, right? They're actually really straightforward in terms of what the products and reactants are, right? So let's actually go a different route. Okay, so first of all, you're going to be making an alkene through these reactions. Okay, and really they're a way to convert a carbonyl group to a carbon-carbon double bond. Right, so this is going to be starting out with this carbonyl group. And then you have this C6H5P. Okay, so let's go over why these two will react sort of the way that they do here. Okay, first of all, these 1, 2, 3, 4, 5 carbons, these are the ones that were originally in my carbonyl group or in my ketone. These 2 carbons here were on the other side of my ELIDE. All right, and so what happens in these reactions is your carbonyl double bond breaks, your phosphorus carbon double bond breaks, and those 2 ends get fused together. In theory, you could also swap these 2 portions. 1, 2, 3, 4, 1, 2, 3, 4 here. Right, because in both cases you would just be sort of severing. However, the preference is to have, this would be way, way, way slower because of the large functional group on that phosphorus. So when you design these reactions, you're going to put whatever the smaller end of your alkene is on your phosphorus. They're really great at creating like terminal alkenes. Seven, 6. Wittig, holy cow, I'm sorry, that was gonna drive me nuts. But these are these Wittig reactions.
Yeah, sorry, I didn't even remember that that was a word.
No, no, you're cool. I mean, me neither, clearly. But yeah, so I mean, that's sort of how you sort of work backwards in the retrosynthesis of those. I would say also, you know, good thing to practice, right? Those Claisen as well as aldol addition in terms of retro synthesis. Those are those problems on the end of exam 2 would pertain to those. How do you write? Part of the problem with those types of reactions that are, you end up with these big ugly products. I mean, you guys did the lab report for 39 and 41, right? You just get ugly products at the end of it. Working backwards to figure out what pieces you needed to combine is something that I would know how to do. What else we got?
I don't remember the name for it, but it's the one you used to tell us looked like the Mercedes symbol, like going from that to a Fisher projection. You remember to do that?
Yeah, that is, what do we call those?
They're Newman projections.
They are Newman projections. Thank you, Sam. God, too many friggin' names.
I was reviewing those earlier.
Nice. Yeah. Okay. I think most important about the Newman projection, right, is you know, kind of this idea of let's work on going the other way first. So if I'm going to look down this particular bond here, yeah, take a second and draw me with that. So again, this is sort of like the front carbon is going to be the one that's on the Mercedes symbol. All right, so hydrogen here, I would put my CH2, CH3. Here's my CH3. You draw a circle. This represents the back carbon, right? So what these are really used for is showing which configurational isomer is the most stable, right? The idea that we want to stagger our bulky groups so they're not directly next to each other. So for example, this would be sort of the most stable projection here. So then if we want to work from here to figure out exactly what the Fisher projection is of this guy, because wait a minute, did I do something wrong here? Yeah, I didn't actually specify stereochemistry here. So here I did though. Yeah, I mean, these are a pain in the butt. So honestly, what I would do is I would look at this and assign these carbons as either R or S in their Newman projection, and then just draw the correct stereochemistry, okay? So for this front carbon here, right, we want to try to be looking at it from this direction, right? So that we can put this hydrogen up top in the back. So see if you guys can't, this is a tough one, I'm not gonna lie. Take a second and see if you can assign stereochemistry for the front and the back carbon, right? Remember the back carbon, by that I'm talking about That's represented by that circle. The front carbon is the center of that Mercedes symbol. I think the easiest thing to do is just sort of try to look at it, you know, in your brain. Imagine that you're looking at it from the underside for the one and the top side from the other. Okay, so how I'm, you know, don't break your back trying to like practice every single possible thing about all these drawing of structures because it's incredibly time consuming. But nonetheless, let's go through how I would solve this here. I'm going to practice. I'm going to first sort of look at this molecule. I'm going to try to assign this green carbon, this front one here, and I'm going to do it by looking in my mind at the molecule this way. Okay. And so just to sketch that out, that means that I would have my green carbon in the middle. I'm specifically looking at it in that direction so that the hydrogen is pointed in the back, right? And if I'm looking at it from that position, that means that my ethyl group is over here. My methyl group is over here. And then on top, I have my blue carbon, which is then connected to a hydrogen as well as CH2, CH3, and then another CH3. All right, that's sort of if I can look at my molecule from this underside here, right? And I'm specifically choosing that direction to put the hydrogen in the back. That's what's going to make it easiest to assign my stereochemistry. So my blue carbon is the highest priority in this particular view, followed by the ethyl, followed by the methyl. All right, so our green carbon, let's just do this. Is what? S or R?
R.
S.
Counterclockwise, right? So this is S. Okay, and then I'm going to do the same thing for my blue carbon, but now I'm going to be looking at it in this direction so that I can keep this hydrogen in the back. Right, so now my blue carbon is at the center. Again, I did this specifically to keep hydrogen in the back. If I'm looking at it from this direction, see if you guys can't do what I did over here if you haven't already gotten it over here. It's definitely tricky. Right, my hydrogen's in the back. If I'm looking at it this direction, that means my ethyl group is over here. My methyl group is over here, and then pointed down is that green carbon with all the crap that's decorated on that. So then if I'm going to go through and assign priority, again, now green gets 1, the ethyl gets 2, the methyl gets 3. This is clockwise. So that guy's R. I'm sure there's other ways of doing it, but at this, if you're going to start with the Newman projection, that's probably the hardest one to start with because assigning R and S is the most difficult there. And then it's really just having practiced being able to kind of move these things around in your mind. I would focus much more on perspective drawings and Fisher projections than the Newman. 99.9% of the time with the Newman drawing, we're not trying to show stereochemistry. It makes stereochemistry a lot more of a pain in the butt to see. Right, so I'm not saying there's no Newman stuff on there. It's just going to be in the context of which one of these conformations is more stable, something like that. So I guess just to finish this off, if I was going to be really good and make sure to draw this molecule here in its perspective form R, so that would be 1, 2, 3. That means that this guy should be sticking out so that my hydrogen can be pointed in the back. And here 1, 2, 3, that's clockwise. So I'm actually going to have this guy be dotted so that my hydrogen's now pointing out at me. All right, but again, my strategy would be to figure out R and S and then just draw that correctly. What else we got?
How about the molecular orbital diagrams?
Sure.
Energy diagrams, stuff like that. HOMO, LUMO, blah, blah, blah.
Yeah, okay, let's think of a good context for this. Okay. So I imagine what you're sort of referring to is when we were talking about them within the context of aromatic compounds.
Yeah, just because I a couple questions like, which is the rate determining step, and blah blah stuff like that.
Well, I mean, rate determining step is going to have a lot to do with what's slower, not the slowest step, not necessarily with HOMO LUMO sort of stuff. Let's just look at this real quick. What you're going to see in these type of diagrams is a molecular orbital diagram. So for example, if we're going to do an aromatic compound like benzene, this has a molecular orbital structure that looks like this. Remember, I think the most important thing is that we've got 6 atomic orbitals we're going to combine. That's the p orbitals on all 6 of these carbons. And that's going to give me how many molecular orbitals?
6.
6, right? So that's an important thing to remember. You get as many molecular orbitals as you have atomic orbitals that you've combined. And now I have 6 electrons that I'm going to go and fill in here. Just like always, we start at the lowest one and then we double up. We get 2 that are at the same level. So we got to fill those half in first. And then we get the other 2 to put in. Label the HOMOs and LUMOs on my little diagram here. Right, so what does LUMO stand for?
Lowest unoccupied molecular orbital.
Yes, this is the lowest, other keyword being unoccupied molecular orbital, right? So in terms of my LUMOs, those would be those there. Okay, my HOMO is the highest occupied molecular orbital. The other thing that comes to mind when we're talking about HOMOs and LUMOs, like when that really comes up, is also through absorption. All right, so in absorption spectroscopy, I'm sending light into a sample of, for example, benzene, and what's happening? The light's going to be absorbed, but why? Nobody? Has everything to do with these HOMOs and LUMOs. Right, so this is because light is going to be absorbed because it's going to excite an electron from the HOMO to the LUMO. Right, so that's why molecules will absorb light, is because they'll promote an electron that's in the highest occupied to the lowest unoccupied. They'll excite that structure, excite the electronic structure. So if I'm going to send in, so oftentimes how you will see this is something like this, where this electron is going to be moved up there because of H nu, which, remember, when we see H nu, we think light, right? So this is sort of an illustration of absorption. Oops. Right, promoting an electron from the HOMO to the LUMO, that is the process of using light, that is the process of absorption. Now, if we have an excited electron that comes back down and it emits light, what do we call that?
Emission spectroscopy?
Yeah, emission and emission is like the super general. Usually it would be fluorescence or phosphorescence, depending if it's a triplet state or a singlet state or other complicated crap that we don't really know about. But absolutely, then you're looking at the emission spectrum. But that's really what I think you'll see HOMOs and LUMOs. The context that you'll see them in is usually in like a qualitative description of what's going on when you're talking about absorption. I guess actually the other one is, and this is, oh, where was that? Chapter 8. Who is that guy? Absolutely. The other context that we saw these in was in these Diels-Alder reactions. All right, and this is going to take place between a diene and an alkene, specifically a conjugated diene, a 1,3 conjugated diene. Does anybody remember what happens in these types of reactions?
You get a ring.
Yeah, you
Yeah,
get a
yeah.
ring. Absolutely, right? So this is like this cyclic firing squad that goes on here, where this pair of electrons comes up here, this one comes down here, this one reaches out here, and at the end what you get in this particular case would be something like this. Maybe this is the context in which that was happening. The argument for why these reactions take place in the syn addition that they do is because the HOMO of your one reactant is lined up perfectly with the LUMO of the other reactant. So that might have been, that was, I think, the only other context that we kind of talked about that. And I'm not going to try to draw this picture, but if you look on page 357, there is a great illustration for the alignment of the HOMOs and LUMOs that, again, I don't want to try to draw now, but page 357 of your book has a good illustration of why that reaction happens as a syn addition. Again, the argument being HOMOs and LUMOs lining up.
Can we go over stereoisomer, like enantiomer, diastomer, and meso kind of stuff?
Like the definitions?
Reaction or yeah.
Yeah. So first of all, stereoisomer, actually, let me see if I can't, there's a really good like flow chart in your book. Basics. What do we do? Stereoisomers. So your alkenes. Oh, so yeah, your stereoisomers. Here we go. So this will be page 144. There's a bit of a flow chart that represents this well. But yeah, so enantiomer and diastereomer are not exactly on there. So stereoisomers are isomers that have same connectivity, different spatial arrangement. Okay, so a good example of something that is not a stereoisomer would be a tautomerization, right? So from enol to ketone, this is a good example of what's not a stereoisomer. These are what are called configurational, and that is because they have different connectivity of atoms. Here, the hydrogen is bound, both of these have the same formula. So this is, what is this? 1, 2, 3. I'm gonna make this molecule simpler so I don't have to do very much math here. Right, they have the same molecular formula, so they're isomers, but they have a different connectivity of atoms. Here, the hydrogen is bound to this oxygen, whereas here, that extra hydrogen is bound to that carbon, right? So these would be configurational. If you have the same connectivity of atoms, then you're a stereoisomer, okay? Two types of stereoisomers. So let me just get rid of this real quick. Are enantiomers versus diastereomers. Okay, both of these would be considered stereoisomers, but they're different types. Enantiomers, so now you're talking about a pair of molecules. A pair of molecules will be enantiomers if they are mirror images. So a good example of that would be something like that versus that. Let's see, 1, 2, 3. This would be S, 2S, 2 chlorobutane versus 2R, 2 chlorobutane. All right, those would be enantiomers. Diastereomers are not mirror images. but they're still stereoisomers. And the way that this would work out is, for example, something like, these are always going to have two stereo centers, but they're not mirror images of one another. So for example, this one here is 1, 2, 3. So this guy's R, right? 1, 2, no, I lied. Yeah, no. This is S, this is R, this is S, this is S. So these would be considered diastereomers. If I had flipped both of these bonds, made them both wedges, now they're mirror images. These are enantiomers. If I only flip one, that's what makes it a diastereomer. Right? So this is SR versus SS. I guess if I just want to stick with this same example to make it very clear. Right, so one of these pairs is a pair of enantiomers, that's these guys here. The other one is a pair of diastereomers, that's that guy there.
Enantiomers can still have two stereocenters. But
Absolutely,
they
as long as they're mirror images of one another.
Gotcha.
And you're only ever going to have a pair of enantiomers, right?
I do have one question. Just
Yeah.
I know we're running short on time. I just have one more question.
You're good.
How this extends to meso compounds?
Oh fuck! What were mesos? Mesos were.
It's like I looked it up, but it's like if they're
So
not
mesos
enantiomers.
have stereo centers, but their mirror images are the same. Their mirror image is identical. So one example would be, I think, would be something like this. Versus this. These are mirror images, right? If I took a mirror and put it down there, I would get this reflection, but these are actually the same molecule. Because of the symmetry about this bond, if you can imagine, I just picked up this whole thing and flipped it upside down, I would get this same molecule. So this is a meso because it has stereo centers. God, you guys are quizzing me on all this first semester crap. I don't remember. Has stereo centers, but mirror image is identical. And they are molecules that have a lot of symmetry. Again, you can always tell because they have symmetry about where those two stereo centers are.
And that's different from the enantiomers because they didn't have a symmetrical bond between their stereocenters.
Correct. Those two enantiomers were distinct molecules. There's no way I can take one enantiomer and spin it around and get it to match the other enantiomer exactly. Meso compounds the exact opposite. I can take the mirror image structure, but then I can take that and spin it and I can get that same one back again. I think the easiest thing with all these is if you have those model kits, play with these examples and can kind of convince yourself of that. I know I said it before and I don't know that everybody has a model kit, but I remember thinking that this stuff was not bad and then I got my butt kicked with it and I got myself a model kit and it made a lot more sense. Of course, it'd be nice if we had access to GRASP and model kits that were, in the classroom, but of course that's not the case.
So meso groups are optically inactive, right?
Correct. So optically active means has enantiomers. well, really just means mirror image, not superimposable. Meso compound, I guess is identical. Another way of saying that is superimposable. So if we use all of our, another way of saying that is octavely active means that it has an enantiomer. Enantiomer. I guess just another note, because I didn't say this before, but I really meant to. The final exam is 45 questions long. Okay, and you will have 70 minutes to complete it. Works out to about 1.5 minutes per question.
So 1 to 210. And we
Correct.
are done at 210.
Yeah. Your organic chemistry careers will be done 2:10, probably 2:15, because realistically it'll probably take us 5 minutes to get started. But yeah. You guys have any other questions?
Probably, but none that I can think of right now.
Yeah, well, I mean, I'm going to be doing nothing but playing Final Fantasy and grading lab reports until final exam time on Thursday. So please feel free to contact me if you guys have any questions. We can always hop on Zoom real quick and run through a problem or something like that. So yeah, if you guys do run into any problems when you're studying, just let me know.
Are you playing the remake?
Yeah, and I never played any of the original ones, but I saw my partner playing the remake and I was like, that looks awesome. And it is.
Yeah, the trailer looked pretty cool.
It's pretty badass, yeah. Big fan. It's consumed way too much of my life in the past 24 hours, but whatever. Cool? All right, so yeah, so please, honestly, hit me up if you guys have any questions at all. All right, you have until this evening to turn in that take-home exam. If you don't turn it in, it doesn't count it against you. Really, if you're happy with your grade, it's not really necessary. If you want to bump it up, go for it, right? But yeah, that would be due this evening if you guys are planning on doing that. Cool? All right, good luck finals week. Everybody, good luck in all your other classes as well. And I will see you on Thursday for the last time. All right, have a good one.